On a minor planet orbiting a yellow dwarf star in a galaxy not very far away, the Virgo Consortium are meeting to divide up the universe. Meet the Virgo Consortium, happily not a race of galactic tyrants, but a less than threatening group of cosmologists who've just created the world's biggest ever computer model of our universe. They're meeting at the Max Planck Institute for Astrophysics near Munich to decide what research to carry out using this extraordinary new resource. The Millenium Simulation has been 5 years in the making. The director of the institute is Professor Simon White.
Everybody's busy discussing at the moment to decide what projects we can do with these data and who's going to do it. So all these young people over here have been sitting down and discussing what they'd like to do and what we think could be done, and then we have to sort out who's going to do what to make sure we don't end up with 2 or 3 people all trying to do the same thing.
So why do we need a simulated universe? What's wrong with the real one we've been looking at with telescopes for hundreds of years?
We've advanced because telescopes have allowed us to get a much clearer view of distant parts of the universe. They allow us to detect objects very faint indeed and very far away. But of course, in astronomy and cosmology, we have 2 real handicaps. First, we can't do experiments, obviously, on our subjects of study. And secondly, changes in the cosmos are in general very slow. Evolution takes millions, even billions of years. And in order to make sense of it, to see how it evolved, we are very much helped by being able to, as it were, study a virtual universe in our computer.
He's looking at the structure of the angular momentum for the well-resolved halos.
Angela's going to look at correlations between these parameters. Like
Simon White's long-term collaborator and joint founder of the Virgo Consortium is Carlos Frenk.
Right, and then...
Brought up in Mexico, he now heads one of the world's leading computational cosmology teams at Durham University.
Astronomy is an empirical science. The cornerstone are observations, data like those data that can be collected, that are being collected as we speak by this magnificent telescope, Jodrell Bank, behind us at Manchester University. Valuable and crucial as the data are, they only paint a limited picture of the universe, because in cosmology, the data just give us snapshots in cosmic history. It is impossible with data alone to understand the interconnections between objects, galaxies, quasars, seen at different epochs in cosmic evolution. The role of simulations is to join the dots, to give us a seamless story of how the universe evolved from the Big Bang to the present, connecting objects that we see with telescopes at early times with those we see with other telescopes at more recent times.
To create a virtual universe, the computer first needs an accurate picture of the early universe as a starting point. Fortunately, cosmologists know this from the faint echo of the Big Bang still visible to radio telescopes. This reveals that the early universe wasn't smooth, but grew increasingly lumpy as infinitesimally small ripples in space and time were stretched as space itself expanded. Frank argues that these tiny fluctuations are the seeds of the galaxies we see today.
So what the simulations do is they take these initial conditions as verified by studies of the heat left over from the Big Bang and apply the laws of physics to see how these tiny little seeds, and they're really tiny, how they grow throughout 14 billion years of cosmic evolution, resulting in a universe like the astonishing universe in which we live. And I can tell you there's nothing more exhilarating than seeing a universe come out of your computer looking just like the real thing. It is truly exhilarating, and it's also humbling.
The Millenium Simulation is 10 times bigger than anything done before. Even so, a whole galaxy can only be represented by 1,000 or so dots. Each single dot in the middle of this image represents tens of billions of stars. Zooming out to an area of the universe 2 billion light-years across required 10 trillion calculations on 10 billion particles. Although Simon White had access to Europe's then biggest supercomputer at the Max Planck Institute, it still had to be closed to the rest of European science for a whole month while it did the Millennium sums. And then there was the software challenge. Problem number 1, computers can't count as high as 10 billion.
It's kind of similar to the year 2000 problem, right? You overrun a counter and you're back to 0. And that happened when we just counted our particles. We can only count up to about 4 billion, and then a normal computer flips over back to 0. And so we couldn't really number our particles except by using more storage space. We had an enormous amount of memory, actually, 1 terabyte. These are 1,024 gigabytes, but this was still a factor of about 2, not enough to fit 10 billion particles. We had to devise new algorithms that are more efficient, and there we came up with new tricks that saved us this excess memory that we didn't have.
Even with these new tricks, the simulation still had some nasty surprises.
Actually, this announced 1 terabyte of memory turned out to be a too conservative estimate in a sense. That's in theory available, but it turned out that in practice we couldn't use all the memory because the operating system needs a fair chunk of it. And in the initial design we didn't know that. So the simulation was running, and as the universe evolved, we came to a point where we now hit the ceiling, which was kind of lower than we expected. And I had to kind of compress some part of the simulation data on the fly.
I'll never forget the time when I rang Volker Springel, who was the man on the call face, and came up to the phone and said, "Look, I'd love to talk to you, Carlos, but I'm really tired, obviously." And I said, "Well, what are you doing, Volker?" And he said, "I'm performing open heart surgery on the computer code that's running the Millenium Simulation. Can I call you back later?"
I couldn't allow any mistake in that. Otherwise, I would, well, potentially I could have screwed up everything we had up to that point.
And that was just the memory on the computer's own chips. The other problem was how to offload the vast amounts of data generated.
The total amount of information we had to store in order to keep working with the simulation is about just over 20 terabytes. So that's 5 trillion numbers, I guess. That's a lot. That's well, that's 1,000 numbers for every person on the planet. That's one way to look about it. So since most people can't remember 1,000 numbers, this means it's more than everybody on the planet could remember, even if they all tried really hard.
For a couple of months, it was a daily struggle with the computer. And you have to be very careful that all of these 100,000 data files are safely stored away before you delete them.
Now safely stored, that data is expected to keep cosmologists busy for a further 5 years as the real value of the project is realized. The Virgo Consortium does have some North American partners, but even so there's unspoken pride that a largely European team have produced a world-beating simulation ahead of often better-funded US programs. Given that, there's universal agreement that the Millenium Simulation will enable cosmologists to test and refine our theories of why our universe is the way it is.
It's marvelous how much data observers have got, but they've been somewhat frustrated because they can't compare this data with any theories. And now we have the Millenium simulations, we have the predictions of the theories in enough detail that we can now see if we have a meshing together of the way the world actually looks on its largest scale and the way we expect it to look according to our theories. So it's a way to actually check our theories. It's an exciting period in the subject. It will allow us to settle many long-standing mysteries. And of course, as always in science, will open up new questions about what will be the fate of the universe and what happened before the first few seconds. All these questions will open up as we solve the old questions.
What I find important about these simulations is that you can look at the universe as it is now, or the local universe as it is now, and you can ask, what were those galaxies before they became what they are now? We used to think that our galaxy collapsed out of one giant lump of gas. We now think it's the result of a large motorway pileup. That other galaxies have fallen into each other, and the resulting mess is us.
Professor Spark believes the simulation's dependence on the Max Planck computer highlights a fundamental funding problem in British astronomy.
In Germany, they give the directors of these institutes a lot of resources and a lot of autonomy, and they say, go do something great. What would need to happen for a project of this kind to be feasible entirely inside Britain is that the Particle Physics and Astronomy Research Council, in addition to providing funding for large computers, would also have to have a mechanism for people to come to them, or a group of investigators to come and say, we need to do this project over a 10-year period, we need stability of funding, but at the same time you have to let younger people or people who want to run a smaller scale project get the funding to do that. And it's very difficult to strike a balance, and even more difficult when you are so stuck for money that it's all got to go on keeping the telescope running that you spent several hundreds of millions to build.
Across the road from the Astrophysics Institute, Germany is already building a vast 8-story home for its next generation supercomputer. In time, it'll host the next generation of cosmological simulations. Until then, the Virgo team have their work cut out analysing the Millennium data. The most pressing research will be into the newly discovered mysterious force that makes up 70% of the universe.
One of the most remarkable discoveries about the universe in the last few years has been that the expansion is speeding up and not slowing down. That's a surprise because we expect that gravity, which attracts everything to everything else, would gradually slow down the expansion. This speeding up, this acceleration, indicates there's some new force over and above gravity. And the nature of this force is a complete mystery. It's as though even empty space exerts a mysterious force which dominates on large scales. This is sometimes called dark energy. We've no idea what it is, but one thing I think we're sure of is that if we understand the dark energy, we'll have solved one of the deepest mysteries of science, namely the nature of space and time at the real bedrock level. We understand the force of gravity. Einstein taught us that. We understand the nature of atoms. They are governed by the so-called quantum theory, which again we learned about 80 years ago. But to understand the bedrock nature of space and time, we need a new theory which somehow subsumes both Einstein and the quantum theory. Because we suspect that on the very tiniest scale, space itself has a structure, a sort of graininess, a very complicated structure. And that means it's not just vacant nothingness, it's got a lot of complexity. And the main observable outcome of that complexity is this so-called dark energy, this force which actually governs the entire dynamics and fate of the universe.
Understanding dark energy is the biggest challenge in physics today. Sir Martin Rees believes the UK is leading the way.
The UK, of course, has a very fine tradition in astronomy and cosmology, and I think that's been reinforced in the last few years in two ways. First, the European Southern Observatory, in which we participate, is undoubtedly the world's #1 telescope. There's no doubt about that. Secondly, these Millennium simulations are the world's best simulations, and I think this has given us a real lead in what I believe is one of the scientific endeavors which, when the history of science in this period is written, will prove to be one of the highlights.